Hi, my name is Justin Tracy. I'm the Advanced Process Manager at LaCour Precision Optics, and I'm here today to talk to you about precision ASPHEREs, their manufacturing, and their metrology. And my hope is that by having a better understanding on how ASPHEREs are manufactured and how they're measured, you can design a more cost-effective, more manufacturable ASPHERE and still meet your performance requirements. First, a little introduction on basically what an ASPHERE is and some of the differences from a sphere. So a spherical surface, of course, the radius of curvature is the same across the whole surface. An ASPHERE has a constantly changing radius of curvature, and the shape is defined by an equation that contains the vertex radius, your R value here, your conic constant, the K, and various expansion coefficients, which may or may not be present relative to the distance from the center of the part. And there's other forms of this equation available. There's the Forbes polynomials, whether it's QBFS or QCon, are also popular. But this equation is kind of the old standard tried and true that is still in common use. You can certainly use the Forbes polynomials, and they have some advantages. But some manufacturing equipment and metrology equipment can't use them, so it needs to be converted. But from a design standpoint, I would use what works best for you. And using this equation, you can design just about any shape you want. It could be a simple parabola, as we have here. You have ASPHEREs that are basically plano in the center and have very steep curvatures at the edge. You can have inflection points. So at the center here, we have a convex radius of curvature. By the time we get to the edge, the local radius is actually going concave. And you take that to the extreme, you get your gull wing, where the sag actually inflects as well. So your convex here, your concave here, and your sag is actually going back up towards where the center is. And these are all manufacturable, but they'll have different challenges involved in their manufacturing. A little bit of terminology that'll help us along later in the discussion. When we're talking about ASPHEREs, you have your vertex radius, which was defined in the equation, and that only applies at the very apex of the ASPHERE. Along the rest of the ASPHERE, that radius is constantly changing. We also refer to what we call the best fit sphere, and there's different ways of defining it. The most common method is that's the spherical surface that matches at the vertex and the edge of whatever aperture you're looking at for the ASPHERE. So if you look at the best fit sphere over the clear aperture versus the part diameter, they could be different, and the manufacturer will choose what works best for them. There's other definitions people sometimes use for the best fit sphere. This could be the sphere that is closest to the curve but doesn't require any adding of material, if you will. So say in this case, if we measure a best fit sphere from the center to the vertex, we'd actually have to add glass to that best fit sphere to make this ASPHERE, which of course we can't do. So instead your blank would be thicker. Okay, that best fit sphere is not going to make a whole lot of sense in that case. There's a few other ways of defining the best fit sphere, but the vertex and edge matching are the most common and what we'll generally use here. Related to the best fit sphere is your departure. So the departure is the difference from your actual aspheric surface, the blue line here, and your best fit sphere, or the orange line. And that's in the Z direction. Not normal to the surface. And that gives you an indication on how extreme of an ASPHERE you have. So people will often talk about how much departure does the ASPHERE have. It's certainly not the end-all be-all of how challenging an ASPHERE is, but it gives a good idea. You know, a low departure ASPHERE of, say, 5 microns, okay, it's probably going to be easy to make. If it has 2 millimeters of departure on a 50 millimeter diameter part, there's probably going to be some challenges in there. Speaking of challenges, so what are the challenges when manufacturing an ASPHERE that makes it so different from a sphere? Well, one of the big ones is you're constantly changing local radius of curvature. That means you can't use traditional tools like you'd use on spherical optics. Those tools are designed to make spheres. They're not going to make full contact on an ASPHERE. They might not fit inside the ASPHERE because of the changing curve. You rub a pitch tool on a surface, it's going to want to go spherical, not be an ASPHERE. And here's a plot of an ASPHERE of the sagittal and tangential radii, and you can see they're not constant, for any given parameter, but they're changing at different rates. So you need some special tools to handle that kind of thing. So the solution we use is subaperture processing. So instead of having a tool that's contacting the entire surface or a good portion of the surface at once, we're only touching a little bit at a time, a few millimeters at a time. And that allows us to use tools that are conformable to the surface or cutting just a single point of the surface in the case of grinding. One of the challenges this brings, though, is you can have local radius issues. You saw in some of those ASPHEREs on the previous slide, you had some pretty nasty curvatures at the edge, concave curvatures. And if you imagine here you have your ASPHERE, really tight curve, and this could not necessarily at the edge, it could be anywhere in the part. And you have your grinding or polishing tool, which has a certain geometry to it. And if that local radius is too tight, you just can't get in there. And of course, there's different size tools available to allow you to get into these smaller places. But you can imagine if you're doing a really large part, but it has a really tight local radius of curvature, so you have to use a small tool. Well, you have to use that small tool over the whole part. So it really becomes an extreme test of patience to make that part, to say the least. Another challenge is, of course, the measuring. So the departure from a sphere limits your interferometry options when using a spherical transmission element. So if you put an ASPHERE on your standard interferometer, it would be a perfect ASPHERE, but instead of seeing straight lines or no fringes, you're going to see some concentric rings, depending on how much departure there is. So low departure ASPHERE, such as this one, you could probably get away with measuring on an interferometer. There'll be some retrace errors, so depending on accuracy limits, that may have to be accounted for. But it's something that could be done. You get into more extreme departure, now those fringes are unresolvable by the camera, or by eye for that matter. So it's just not possible to measure such a surface as a full aperture, not to mention the retrace errors you could have in there. So the solution that is most commonly used is profilometry, and there's different variations of that, various contact and non-contact methods. And basically what that will do, and we'll talk about this a little later, is do slices across the part. And that'll tell you how much you deviate from your desired surface. And my hope is, by you understanding these challenges, and like I said, we'll go into some more detail on some of them here, it'll help you design a more manufacturable ASPHERE. So, first step in making an ASPHERE, of course, is to actually grind the surface. So, the idea here is we want to take our raw chunk of glass and we want to grind it with sufficient precision and finish that we can minimize our polishing time. Polishing is where a lot of the issues can come into play with an ASPHERE, whether it's rounding edges or putting in mid-spatial frequencies. So we want to minimize how much time we spend polishing. So basically what we do is we start with our lens blank, just a hockey puck of glass. And from there we're going to grind in our best fit sphere. And again, this could be the best fit sphere that makes the most sense for manufacturing, not necessarily the vertex to the edge, though that is still the most common for manufacturing as well. That does often work the best in that case. But in the case of a gull wing or those parts that are plano over the center, that might not work out so well. So this best fit sphere is cut using generally standard tools like you'd use, say, with a CNC grinder. Just your ring tool comes in, really quick to cut the best fit sphere. Maybe it's even a molded blank that's already almost there. And that removes the bulk of your material from your puck of glass. From there, we need to rough grind the ASPHERE. And there's various tools we can use for that, but they are all single contact tools. So what that'll do is we feed in this best fit sphere, and that tool will follow the contour of our desired ASPHERE, just single point at a time. So instead of coming down as one big chunk taking off glass fast, we're just taking off a ring of glass at a time, basically following the spiral tool path around the part to the center. And if it's an extreme ASPHERE, like in this example, it's very extreme, you may need several passes because you can only take off so much glass per pass. After our rough grind, we're going to do a fine grind. That's going to follow the same tool path as the rough grind, just a little bit deeper down. The idea here is you use a rough tool to kind of bulk in your ASPHERE, and now you use your fine tool to get a more finely ground surface to aid with the next processing steps. But you are just following the same ASPHERE curvature. And finally, your finish grind, which is basically a fine grind. Sometimes we use special tools to get a higher quality grind than what we maybe use for spherical polishing, just again to minimize our actual polishing time. And in some cases, say it's a very low departure ASPHERE, you may be able to skip some of these steps. You may go right from best fit sphere to the fine grind, which saves time and is quite handy. As I mentioned, ASPHERE grind is a single point of contact. Here's an example of a finishing wheel, and you can see we're just contacting one small area of the ASPHERE at a time. And that's going to do that spiral tool path from the edge to the center. And this finish grind here, just to mention, this could actually take up half the total grinding time. This is the final surface you're going to have before you actually do your polishing, so you want it to be as good as you can get. And to do that, you need very precise control of the process. You want to minimize your form error, your deviation from the desired ASPHERE. You want to avoid periodic structures, whether that's from machine vibration, tool issues, temperature issues with your coolant. If you have fluctuations in your coolant temperature, that can imprint in the ASPHERE. You want to avoid all those. So we generally use very specialized machines for doing this. These are dedicated machines. They're only designed to grind ASPHEREs. And they're very precise just for that. Now, of course, doing the single point of contact, you have much longer processing times than you do with spherical optics. Instead of bulking out everything, coming down with your ring tool like we do for the best fit sphere, we're single point cutting this ASPHERE. That takes some time. And we may have to go several times. We might have to do the rough grind, a fine grind, a finish grind. And the rough and finish grind might be several passes even. So that can be an issue. So having lower departure ASPHERE certainly helps in that regard. Keeps the time and cost down. And for doing this grinding, as I mentioned, we have various tools available. Here's a sampling. We have a couple of traditional ring tools like you'd use on a CNC machine for grinding. But if we're grinding the ASPHERE curve, we're actually just using the edge of it. So we tilt the tool instead of coming down as a ring on the part. We're just using the edge of it and using it as a single point cutter, basically. We also have various discs or wheels we can use, ball tools for getting to some tight curves. So there's an assortment of sizes and varieties of tools. Every ASPHERE is different how you're going to approach it. And that's why we have a large selection of tools available for that purpose. So of course, after grinding, we need to polish the ASPHERE. We need something we can use, not just a ground piece of glass to look at. And the purpose of polishing is we want to remove that grinding damage. We want to smooth the surface. So, even though we do our best in grinding to have minimal, say, mid-spatial frequency marks or tool marks, what have you, what is there, we want to be able to smooth out so you don't have a ripply surface. And ideally, we want to achieve our final form specifications. If you want a quarter wave ASPHERE, we want to get a quarter wave ASPHERE here. So the first step in the process is to do the gray out. So here we're taking our ground surface, our finished ground surface, and polishing it, removing all that damage. That's our first priority. Ideally, and if the specifications are such it allows it, the part might be good after this step, which is great. But we go from our ground surface to our nice polished surface, a good optical surface. Then from there, we're going to do figure corrections. And what we do there is we measure the ASPHERE. What does it look like after gray out? And we feed that into the machine. So this is what our part looks like after gray out. We have some astigmatism. Okay, we need to correct that. So we feed that into the machine, and we achieve our wonderful surface that meets all the specifications you could ever want. And just like grinding, ASPHERE polishing is a sub-aperture process. So here's one of the potential polishing tools. It's a fairly small tool, just has a little contact area there. And just like with the grinding, that's going to follow a spiral type tool path from the center to the edge, or maybe go back and forth. There's a few different techniques you can use there. But it's only polishing a small area at a time. And this tool here is actually conformable to the surface. So usually in this case, it's a polyurethane pad, and behind that there's some foam. There's different rubbers people can use, and what that allows is the tool to conform to the surface. So as that local radius changes, the tool is also changing to match that surface. If you just had a rigid tool, you're going to have a lot of mismatch between the tool and the surface, and bad things will happen. One great thing about the sub-aperture process, though, is it allows deterministic processing. So what I mean by that is, as I mentioned, we can feed this data map, our measurement of the surface, into the machine. The machine has a model of the removal function. Different machines do it differently as far as the modeling goes. But then the machine can calculate what's the tool path I want to use to make that part good. So as it's doing this spiral tool path, it'll move very quickly over these low areas. And we can see these high areas, the tool is going to slow down and take off more material here. And as you spiral towards the center, it will change that speed constantly and allow you to correct that astigmatism. So there is definitely an upside to the sub-aperture process. It allows for very precise control of your irregularity. But just like with grinding, you have increased polishing times. It takes a long time to remove the grinding damage when you're only polishing a little area at a time instead of the whole surface at once. So there are certainly longer times. And again, the higher the quality your grind is, the lower your polishing times will be, which is why we kind of harp on the grind so much. And there's various technologies and tools available from several different CNC manufacturers. And there's a lot of homegrown tooling as well that people use to manufacture or to do the polishing of the ASPHEREs. Here's the foam pads with the polyurethane pad, as I mentioned. Here from Optical, we have their UFF, where it's a rubber wheel of different durometers depending on what you're working on. And you have belts that have the serum oxide impregnated, or maybe you use a polyurethane belt with a slurry. There's, again, many different ways, and we decide when we're manufacturing what's going to work best for this particular ASPHERE based on the shape and the material and the specifications. So, and we might use one of these tools. We might use all these tools on any given ASPHERE. You know, a big one for the bulk and a small one for the fine correction. There's a lot of different combinations that are possible. And of course, each has its own strengths and weaknesses. Some are great at smoothing. Some are better at figure correcting. So we might grade and smooth with one and then correct with a different one. And we're always balancing the hardness of the tool, trying to balance that conformability to the surface. Yet if it's too soft, you're going to kind of ride over or ride with your ripples from the grinding and not really smooth them out. You're just going to polish them. So you have polished ripples instead of smoothing them out. But too hard of a tool, you can leave track marks and things like that. So it's a balance trying to find the right tool for the job. So finally, once we're done with that polishing, we need to finish the ASPHERE. And this is kind of an optional step. It may or may not be needed. Ideally, after that previous correction step with your ASPHERE tools, the parts and specifications, and the part gets shipped on to the next area. But sometimes we need to correct areas that are kind of beyond the capabilities of these machines. So the most common method of doing that is magnetorheological finishing, or MRF, from QD Technologies. It's a very common method. There are things like ion beam finishing, and people have various kind of hand touch-up techniques for a very, very skilled operator. But MRF is by far the most common. And again, this is a sub-aperture process. You can see here we have it's basically a magnetic fluid with a magnet on this wheel that's spinning around. And our part comes down, is also spinning, doing a spiral tool path. It doesn't actually hit the wheel, but that fluid squeezing between the part and the wheel creates basically a polishing lap and does your removal. And one of the things that makes MRF so powerful and why it's a finishing tool is that removal function that's in between the glass and the wheel is characterized with an interferometer. So we know it very precisely. We have a very precise measurement of the part, and the computer can then calculate exactly how to move and fix those. So you can just get a super high quality part. Generally, the roughness is also better than what you would achieve off the previous polishing step. So it can also improve roughness, not just your irregularity. One limitation it has is you can't use it for, say, grain out or smoothing, because it is a very conformable tool. So as I mentioned before, if you try to polish a ground part with this, you'll generally end up with just very shiny ripples on your part instead of removing the ripples. So you do still need those previous steps. This is not a do-all polishing tool. It's an awesome finishing tool, though. And your precision here is often limited by metrology. Not always, but that's commonly a limit. If you can measure the error, you can probably get a removal function and correct the error. And in the case of very low departure ASPHEREs, it's hard to put a firm number on it because it depends on the size of the ASPHERE as well. But, say you have kind of under 5 microns, maybe under 20 microns in some cases, or 30. You can actually take a best fit sphere polished using conventional methods and use MRF to generate the ASPHERE you want. And that generally results in a very smooth, very precise ASPHERE. So, that's something to keep in mind when you're designing the system. If you can put in a couple of low departure ASPHEREs that can be done with MRF versus one more dramatic ASPHERE, if the smoothness of the surface is critical, that's something to really consider. As I mentioned, with MRF, you can basically make the part as good as you can measure it. And that's in any manufacturing too. If you can't measure it, you really can't make it. So how do we measure the ASPHERE? As I mentioned before, the most common method used right now is profilometry. In this case, we have a single contact point, and that is going across your optical surface. And the computer knows what the shape of the part should be, and from there determines, okay, this is the error from the ideal shape, is this curve here, and that slice across from the center through the apex to the edge of the part. And this is simple. It's fairly precise. The main limitation, kind of two limitations. One, you're contacting the part. So for very soft glasses, you need to consider the potential of damaging the part. But generally, that's not an issue. But also, it could hide asymmetry. If you have astigmatism, you're not going to see it on a single slice because that's a radius just along that one axis. So it'll just show up as maybe a vertex radius error. Or if you have coma in the part and you measure it just the right angle, you might not see the coma. So there's some definite limitations of 2D profilometry. So kind of the option up from there is to do some 3D profilometry. And that could involve just doing these single slices at multiple angles, and you can stitch them together. There's some software to do that. And that gives you a pretty rough idea of the errors in the part. It's not perfect, but in many cases, it's good enough. Or you can do 3D profilometry, which there's machines that do raster scans with a contact profilometer, or what we use at LaCroix. We have a non-contact sensor here that does a spiral toolpath, just like for polishing and grinding, and it's taking data as it goes along and gives you this map of the ASPHERE and or the error in the ASPHERE. And so from that, if it doesn't meet specifications, we can feed that into our polishers or our MRF finishing tool and make the part better. In some cases with ASPHEREs, as I mentioned, you can do interferometry, especially with very low departure ASPHEREs. Other options available, especially for conics, you can do various null lens setups. Some of those are straightforward, some of them are challenging. Some of them you can't see the center of the part when you do it, so there are limitations there. And there's also various stitching interferometers available that can measure some ASPHEREs very precisely. One of the advantages of profilometry is that it can measure very extreme shapes. Gull wings are just as easy to measure with one of these as basically a spherical surface would be. So these can measure dramatic shapes that, say, a stitching interferometer couldn't. So there's a lot of versatility there. And kind of on the same lines of metrology, one thing that's important to be aware of with ASPHEREs is mid-spatial frequencies, or MSF errors. So this is kind of the in-between errors. Everyone has their own definition on what they consider to be a mid-spatial frequency. Whether it's what it looks like after Zernike terms are removed or however many cycles across a part. And it's going to depend on the design, what's considered a mid-spatial frequency, and even if it matters. If it doesn't matter in your system because of the design, then don't specify, because that's an extra manufacturing challenge and it can up the cost of the part. But if these types of features would be a problem in your system, absolutely. Make sure you put a specification on there, and we'll talk about that in a minute, different ways you can specify that to make sure we're controlling those errors properly. Here's some 3D examples of mid-spatial frequencies. Here's some profilometer traces. Here we have this orange one, has very low mid-spatial frequency errors, just some spherical aberration. And this blue line that's all wavy. And really, peak to valley wise, they're identical. RMS wise, this blue one's a little bit better. But in some systems, that rippliness will just kill your performance. So you want to put specifications to make sure you get something more like this orange line and not that blue line. Even though if you just give a peak to valley specification, they both might be good. And the cause of this is that subaperture processing. That's one of the disadvantages of subaperture processing. Every tool has its own kind of characteristic. So we choose tools to try to minimize mid-spatial frequencies and adjust process parameters appropriately as well. And, if these types of errors are going to be problematic for your system, make sure you put specifications on them. Talk to us. We can help you come up with a reasonable specification as far as what would be manufacturable, what reasonable numbers are in that given part. Some common examples I see a lot are, this is by far the most common, is to put a max slope, either peak to valley or RMS on say on the profilometer trace. So say 0.2 microns per millimeter over a 1 millimeter window. So that's 1 millimeter along the trace. The slope has to be less than 0.2 microns per millimeter all across the part. And that's a fairly common specification. You have to be careful choosing your window size. Too small, then metrology noise becomes a problem, and we can certainly help you with that. Another common thing is to just have a specification. Okay, remove the first 36 Zernike terms or the spherical Zernike terms, whatever you wish. And after you remove those, I want there to be less than however many microns RMS of residual error. So, for example, you remove all your astigmatism, spherical error, you're left with this map. You want this data map to have less than that amount of error. That's also a fairly common specification that works quite well. And you can also do specifying your maximum error in various spatial frequency bands. That's less common. It's more difficult from a manufacturing perspective to say, yes, I can do that, or no, I can't, because everyone does those things so differently. But if that's what's necessary, we'll do our best to work with you and make sure you get what you need to have good performance. And that's any manufacturer, just, whether it's us or somebody else, hopefully us, make sure you talk to your manufacturer and make sure you're specifying what you need to specify and that they can make that. And the earlier you do that in your process, I think the happier everyone will be in the end with the whole process. Well, and that's all I have for now. I appreciate your time and letting me talk to you about what we do to manufacture and measure your precision ASPHEREs. Feel free, if you have any questions, to contact us, whether it's myself or our sales engineers. We'll be more than glad to make sure you're getting what you need for your system to perform. Thank you very much.